Hello and welcome to video number 59. We just got started with chapter 9. The last topic actually of this entire quarter is under this title of the analysis of variance. It actually goes into chapter 10, but it's really under the same umbrella. And what we're trying to do is compare multiple population means. That's basically what we're after here, and we're beyond two means. And so this is the example I want to remind you about here. It's on organic methods, and we're growing sweet corn, and we're looking at the effects on sweet corn when using these types of organic treatments. Nematodes, wasps, bacteria, and control. Here's the schematic on what's going on underneath the hood. If you think about what's the population, the various variables, corresponding normal distributions, and if you notice something, we have different means for each of the normal distributions, but we do have a common standard deviation. That's not by accident. We're doing this intentionally, something we could check a little bit later on. And we have, for each of the populations, a corresponding sample, and each sample will yield 3 bits of information. A reasonable set of null and alternative hypotheses here. If we're looking at mu1, mu2, mu3, mu4, all being target parameters from each of the corresponding populations, a null hypothesis that's very reasonable is to do this, right? Mu1, mu2, mu3, mu4, they're all the same. And the alternative is they're not all the same. Right? There's a difference somewhere is what we would be saying. You could just say H naught is not true in that sense. Let's go to the top of the next page here. What you see over here is a set of assumptions from the analysis of variance. Basically, all of this is that picture that we just saw over here. Right? Just a summary of that picture. So please read this. We have K independent simple random samples, one from each K populations. We have population 1 going off of that normal distribution. Excuse me. Population 2 off of that normal distribution. Population K off of that normal distribution. And they all have the same variance. I'm sorry, the same standard deviation, also the same variance. Sigma is the same in all K populations. That is an assumption that we make. There's a way to check on that assumption. And that actually helps make the computations a little bit smoother. Now, I've set the stage over here, so if you could draw these two axes, set of axes over here. What we're going to do is we're going to create a box plot. I'm going to have you participate here. So look at this. We're going back to the nematodes, wasps, bacteria, and control example. It says this, in the space below, draw a side-by-side box plot for the case where 1, data are very consistent with the null hypothesis. So that's case 1 over here. And case 2, data are very inconsistent with the null hypothesis. That's going to be over here. Now, it's been a while since you've thought about box plots, I'm sure. So what are you going to do here? Let me start you off. Remember, a box plot, we'll make it vertical. 5 line segments, 1 for each of the 5-number summary values, and then you connect the middle 3 and you extend out whiskers. So what I'm showing is the non-modified box plot. Do you remember that from like a long time ago? So this is weight. So let's suppose for nematodes, right? The 5-number summary has a corresponding box plot that looks like that. If you remember, this would be minimum, Q1, median, Q3, maximum, something like that. Now, without any assistance from me, I hope you can do this. So I do want you to take some time to do this right now. Give me some other box plots over here for wasps, bacteria, and control under the assumption that the data are consistent with the null hypothesis. Here's a reminder of what the null hypothesis stated. Mu1 is equal to mu2 is equal to mu3 is equal to mu4. So there's not just one answer here, right? If I looked at all of your pictures, they'd all probably be different, but they should have a common thread. So why don't you do this right now? Go ahead and fill in this picture. Right. Hope you had enough time to do that. What would be another box? So a box plot for wasps and a box plot for bacteria and a box plot for a control that's going to be consistent with the means being all equal to each other. Well, if the means are all equal to each other and you know the spread's about the same because of this assumption, all the sigmas are the same, shouldn't that mean all your box plots should basically be on the same level? Now, they don't have to be exactly on the same level, right? You could have a little bit of wiggle, but there should be a lot of overlap. And I think that's the thing that would be our common thread here. So let me do this. I'm going to intentionally jitter this a little bit. Here's the box plot for wasps. Here's the box plot for bacteria. Here's a box plot for control. All right. And you should notice that we've got a lot of overlap. There's a lot of overlap here. In fact, if you look at this picture, if you were to ask me based off of this, which of the treatments seems to be the best, which one seems to be the worst, I'd say they all look about the same to me, right? There's so much overlap here. So this is very consistent with the null hypothesis. I hope you agree with that. Let's come over here. What about box plots where the data are going to be very inconsistent with the null hypothesis? Let me start you off with this one. Same place. Doesn't have to be, but I'll start you off with this. There's your box plot for nematodes. Right. Now here's what I want you to do. Take a moment and put in three more such that the data are very inconsistent with the null hypothesis. There's not a single correct answer here. I think if we all collected our work, we're all going to have different pictures, but there will once again be a common thread. So why don't you do this now? All right. Well, what's going to happen here is what? This has to be violated. They're not all going to have the same centers. If they don't have the same centers, there's got to be some break on the overlap. You can't have this. Might have something like, and here's one example. I'm going to put wasps way up here. I'll put bacteria way down here. Now, do they all have to be staggered? No, they don't all have to be staggered. There must be some staggering somewhere. I hope you agree. I'm going to intentionally, you don't have to change your picture, but for control, I'm going to intentionally overlap that with nematodes just to make the point, right? This picture is very much not in harmony with that null hypothesis, right? I definitely have a break. Can you tell a difference? If you ask me, what would the recommendations be? I'd say, well, in this case, stay away from bacteria. I don't know what it's doing, but it's definitely bringing the weights down. Wasp seems to be head and shoulders above the rest. Nematodes and control seem to be basically the same, all right? So that's data consistent with the null hypothesis. That's data inconsistent with the null hypothesis. I ask a question here. We already know the answer to this. Which one gives weak evidence against the null hypothesis? Which one gives strong evidence against the null hypothesis? Let's write this down over here. This is definitely weak evidence against H0. Please write that down. Whereas this is strong evidence against H0. And we will come back to this picture in a moment. Let's go to the next page, page 172. For this hypothesis testing scheme, we're still going to follow this plan, 5-step process. And in general, let's suppose we have K groups, K treatment groups, right? In general, we will write H0, mu1 is equal to mu2 is equal to mu K. So they're all going to be the same. The alternative hypothesis is what we've written before. Not all mu i's are equal. Once again, if you wrote this for me, I will not take any points off. H0 is not true because that's the same thing here. There's a fallacy somewhere there. They're not all equal signs. That's basically the same thing as saying H0 is not true. So that's your first step, right? Step 1. Step 2, set alpha, that's easy. Step 3, which is usually the most time-consuming part and takes certainly a lot more computations. I'm going to kind of streamline this for you because for this step 3, although there are formulas, you'll see it in our book, there are formulas, but I think it'd be best if we just rely on the software to give us the value of the test statistic. But let me introduce the test statistic here. The name of the test statistic that we use in analysis of variance, ANOVA, is the so-called F statistic. This F is named after one of the most famous statisticians. His name is Sir Ronald Fisher, and that F stands for him, his name. Now, let's come over here, and I want to draw an analogy to what we've seen before. Previously, in the chapter using the chi-square test statistic, you may recall the following. The larger the value of the chi-square test statistic, we have what? We have greater, we have less evidence against the null hypothesis. Please circle that. I hope you selected greater. We definitely have greater evidence, right? Do you remember the minimum value of chi-square was? 0, meaning no evidence against the null hypothesis, but as chi-square got bigger and bigger, you got more and more evidence against the null hypothesis. Well, you'll have to take my word on this. So there's a formula in the book that will show that this is true, but the minimum value of F statistic is also 0. It actually turns out that the F distribution, when you look at its shape, it's very much like chi-square in that it tends to be right skewed, positively skewed, right? So it starts at 0, and the larger the value of the F statistic becomes, the more and more evidence we have against the null hypothesis. So look at this. I've already answered this for you. The larger the value of the F statistic, we have greater evidence against the null hypothesis. Please mark that. So although I'm not showing you what the formula for the F statistic is, I would like for you to add this note. Coming back over here, I said this on the page we were just on. Let's make a note where F seems to be large and where F seems to be small over here. So can you make this note? Here we've got weak evidence against the null hypothesis. What's going to be the value of F? F is going to be small here. So F will end up being small in this kind of situation where the data are very consistent with the null hypothesis. But when the data are very inconsistent with the null hypothesis, you're going to get a large F. It's going to be large and it's going to be positive. Can't be negative. All right. So that is what I'd like for you to add there. Now, let's go to page 173. So coming over here, let's look at some data here based off of this nematodes, wasps, bacteria control example. Suppose the experiment was conducted so that 5 ears of corn were extracted from each of the organic treatments. And here's the data in ounces, and here's the corresponding box plot, right? And immediately you know the following, right? Just investigating this, you could sense the following. First off, do we have strong, moderate, or weak evidence against the null hypothesis? And I hope it's obvious. This is definitely strong evidence against the null hypothesis. Please make that note. What would you anticipate for the F statistic? Would it be large or small? Of course, it should be large. Now, how about this? What would you anticipate about the corresponding p-value in this situation? It should be small, correct? So please make that note. Oh, in fact, let's write it down over here. So we have strong evidence against the null hypothesis. Seems pretty obvious, isn't it? That means what? We're going to have a large F value, which means what? We're going to have a small p-value. So I hope that all makes sense. Let's take a look at here. This is perhaps the most important part of this discussion. For every ANOVA investigation, there is a corresponding ANOVA table. Okay? This is called the ANOVA table. And every software will produce something like this. This table was generated in Minitab, of course. And now I'm going to describe what each of these components correspond to. You'll notice this says source, it says factor, error, total. There's a column for DF. You could take a wild guess what that stands for. It's called degrees of freedom. And this ADJ, can you put an X through that? Not that it's wrong. It does mean something, but for our purposes, we don't need it. So ignore ADJ, please. If you're really curious, ask me during office hours. I'll tell you what that means. But for our purposes, don't worry about it. SS stands for sum of squares. MS stands for mean square. Now I'm going to explain this on the next page so you don't have to write any of that stuff down. There's your F value right there. That's called your F statistic. That's your step 3. p-value. That's your step 4 of our 5-step process. So we're actually going to grab everything from here. We're going to let Minitab compute all of these, but I would like to explain what all of these components are. And so why don't we do that here? Let's go to page 174, please. And over here, before we go too deep into this page, I'd like for you to do the following. What I'd like for you to do is to do a comparison with something that we've seen a long time ago. I don't know if you remember this, but let's do the following. Can you please write this at the very top? Compare with section 3.3. And I'd like for you to take a look at page 63 for a very important relationship that we talked. This is a long time ago, right? This is actually regression. Seems like it has nothing to do with what we're talking about here, but it actually is deeply connected. We had something like this. Do you remember this? SSReg plus SSE is equal to SSTO. That's something I want to remind you about, because what we're about to talk about on this page is very much similar to what's going on there. So let's look at page 63, please. You have your page 63. It should look something like this. So that's the exact same page that we used and we wrote on way back when, section 3.3. And we're talking about this thing called the coefficient of determination in regression. And if you remember, there is this thing that we called SSTO. And if you look at the formula, it contains something that looks very familiar. This formula is really the most interesting part of this formula, which is called sample variance. And if you recall, sample variance is a measure of spread or variability of the variable of interest. In this case, it's y. And so that part right there, we said is that part right there, that's really the most important part of this formula. There's this 1 over n minus 1, that's just an averaging term, right? But that really captures the overall variability in y being the response variable. Now, this was the part I want to bring back to your attention. SSTO represents the total variation in y. I said this before, I'll say it again. Logically speaking, you could break up that total variation in the response variable into 2 components. One is called SS resid or SSE. SS resid or SSE represents the variation in y unexplained by the linear regression. And you could talk about the other component, which would be the variation in y explained by the linear regression. And we represent that with SS reg or SS regression. So this, you see right over here, is the relationship that I hope makes sense logically speaking. The total variation in y, the response variable, can be partitioned into 2 components, right? The total variability in y that can be explained by the regression, and the total variability in y unexplained by the regression. Logically speaking, that should be a perfect partition. And if you add those, you should get that, right? That's the one thing I want to remind you about. The other stuff was about this thing called coefficient of determination. Don't worry about this part right here. I just want you to focus on that and make sure you're comfortable with this partition, logically speaking, right? Total variability in y is broken up into 2 components. Total variability in y explained by the regression, total variability in y not explained by the regression. And we called SS resid back here, but you could also call it SSE, right? And we wrote that over here. Now, what does that have to do with what we're talking about here? Well, in analysis of variance, ultimately, we're trying to describe how much of the variability in the response variable, here it's Cornway, that can be broken up into 2 components: variability explained by the treatment and the variability explained by everything other than the treatment. So that sounds a lot like the language that we used up here, right? So SSTO is equal to SS reg plus SS resid or SSE. We're going to do the same thing over here. Another way to say this is the following. In the response variable that has the variability in the response variable can be broken up into two components, the variability explained by factor, or the treatment that is, and the variability explained by error. Now, our book, we use the term between groups for factor, within groups for error. Now, the reason why I'm using this term factor and error is because in your Minitab output, you're going to see these sources: factor, error, total, right? So that's really for your treatment right there. That's really for everything other than treatment. Come back here. Now, SS, as I mentioned, stands for the sum of squares. And there are three types: sum of squares factor, sum of squares error, and sum of squares total, right? That sum of squares total is just like SSTO. I mean, it's the same business right there. They are basically the same. So can you write this down over here, right underneath this? Please write this down as an interpretation. This is the overall variability in the response variable. So comparing that interpretation to the interpretation we gave back on page 63 of the course notes in section 3.3 for SSTO, it's exactly the same. It represents the overall variability in the response variable. So that has not changed, all right? Now, what's this? Factor that corresponds to treatment, all right? So please write this down. This will be the variability in response variable that is explained. So the variability in response variable explained by the treatment or the factor. Oops, the treatment, right? So that's the variability in the response variable explained by the treatment. SS error or SS resid, I don't care how you want to label that. What would this be? It would be the leftover. This would be the variability in response variable unexplained by treatment, TRT, okay? So think about that. That should logically be a partition, shouldn't it? Overall variability in the response variable. It should be partitioned, logically speaking, into two camps. The variability in the response variable explained by the treatment, and the variability in the response variable unexplained by the treatment. That should be a perfect partition. So could you put this down? There should be an equal sign right there. You know what you should be able to do with these two things? You should be able to add them, right? That variability plus that variability should equal the overall variability in response. Look at this. 43.929. That happens to be the variability. That happens to be sum of squares factor, which you saw on the previous page. This is sum of squares error. You could use your heads or use your calculator, but you can confirm if you add those, that happens to be that. Right? That happens to be 48.172. And they will always add. So if you want to come back to this page, you could make a note. We just talked about this right here, that right there. If you draw a line underneath that, those things do add up. That is the sum. Sum of those sum of squares. Sum of squares factor and sum of squares error. So please add that note. So what we just did is from this so-called analysis of variance table talked about what those things correspond to, what that corresponds to, and at least a heuristic argument why those things got to add up to give you that. Because it's just like the thing that we saw back in chapter 3 under regression. SSTO was equal to SSReg plus SSE back then. Over here, SSTO is now equal to SS factor plus SSE. All right? So we have seen that before. We're not done with this page yet, but I do think this is a good place for us to stop. So why don't we stop here at the beginning of the next video. We'll pick up right where we left off and talk about these other things called degrees of freedom, mean squares, and eventually talk about this thing called F. All right, thanks.